Today I want to start by talking about operators a little bit, okay? And eventually to describe you this code. And my hope is that things will be more clear to you after this. I forgot to open this. So okay. So let's talk about operators one more time. And I will start with a simple one. And before we go too deep, let me tell you something. So as you can see, it matters what you put in this axis, right? Whether you put x or p. Although it's the same, it's the position eigenstate, whether you are plotting it with respect to x or with respect to p, it changes, right? It's a different thing. So what I'm about to discuss is already complicated enough, okay? So I will keep everything in x, okay? Whenever we write a vector, it will be with respect to x. So we start by basically, we start by putting x into a grid. This is our grid. Okay, and there are numbers. There are going to be numbers on this grid, and they will mean something. So, for example, let me start by operator x. What do you think it looks like? Well, operator x has to have this property that when you operate with operator x to a state x, it should return x as a value and x vector as the vector. So these are eigenstates. This is the operator, and this is the eigenvalue. Let me just replace it with eigenfunction. First of all, let me give you some time for this to travel to your minds. Does it make sense? So you have an operator, yes? There's a eigenvector. Let's go with eigenvector. Very good. Eigenvector, eigenvalue, and this is the operator, which is represented by a matrix. Okay? So it's better if I write it like this. So what does this matrix looks like when you discretize x? When I discretize x, what does this x operator looks like in matrix representation? Let me start with something a bit easier. What do you think this vector looks like, x vector? Yeah, it looks like this. It's basically, depending on what this x is, it's like 0, 0, 0, 0, 0, and then there is 1 somewhere here, let's say, and 0, 0, 0, and that point is x. Okay? Let me show you how the operator, the matrix looks like, and it will make more sense. So this is x-axis, and the x can be 0, 1, 2, 3, 4, 5, 6, 7. And I'm writing it actually in terms of something, like, for example, 0 angstrom, 1 angstrom, 2 angstrom, 3 angstrom. Yes? So your matrix looks like this. 1, 2, 3, 4, 5, 6, 7, etc. and these are all zeros, these are all zeros, and this is your X matrix. Okay? This is the matrix that represents position. Why? Let me tell you why. Anybody who knows what are the eigenvalues of such a matrix? Eigenvalues. Minus diagonals or plus diagonals? Like diagonals, right? When it's all zeros everywhere in a matrix, except the diagonals, then the values of the diagonals are actually eigenvalues. That's why this eigenvalue solving eigenvalue equation sometimes is called diagonalization, matrix diagonalization. So we already have a diagonalized matrix, which means that we actually have eigenvalues as 1, 2, 3, 4, etc. Okay, these are the eigenvalues. Let me concentrate on eigenvalue x equals to 3. For eigenvalue x equals to 3, what do you think is the eigenvector? Very good, very good. It is 0, 0, 1, 0, 0, 0, dot, dot, dot. Okay? Only the position where x equals to 3 is 1, the rest is 0. Why? Because you can actually multiply this matrix 1, 2, 3, 4, 5, etc. with this matrix 0, 0, 1, 0, 0, dot, dot, dot. And what are you going to get? You are going to get only this value, right? So you are going to get 3 times 0, 0, 1, 0, 0, 0, dot, dot, dot. Do you see it? Everybody can see it? So the matrix X is represented by this. How about, do you have any questions? No. How about, let's say, Hamiltonian? Oh no, let me move slower. How about V of x? How would you represent it as a matrix? It's the potential, yes. And it's a function of x only. Let me give you the answer. The answer is this. It will be v at 1, v at 2, v at 3, v at 4, dot, dot, dot. Zeros everywhere else. Does this make sense? Yes? Very good. How about kinetic energy? Yes, the matrix, I'm asking for the matrix representation of the kinetic energy operator. It's diagonal again, are you sure? Because remember, this is minus h bar squared over 2m del squared over del x squared. Do you remember this? Do you remember what happened to this one? Delayed? What do you mean by delayed? Okay, I think I have in my notes how it looked like. Just a moment. Okay, it's in the previous notes. So let's just write it down. Do you remember that we discussed del squared over del x squared of f2 was basically f1 plus f3 minus 2f2 over delta x squared? Do you remember this? Yes? So we put this minus h bar squared over 2m outside, but otherwise the matrix looks like this: minus 2, 1, minus 2, minus 2, minus 2, minus 2, dot, 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 1, 1, 1, 1, dot, 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 1, 1, 1, 1, zeros, zeros. Does it make sense to everyone? Of course, I forgot divided by delta x squared. Okay? So this is the kinetic energy, and this is the Hamiltonian, basically potential energy plus kinetic energy matrices. If you sum them up, you get the Hamiltonian. What else could be interesting to us? Momentum operator. This one is h bar over I del over del x, right? Do you agree with this? Actually, I can write it. Okay, let me leave it like this. So how would you represent, actually we didn't discuss this yet, but is it okay if I represent this one as f3 minus f1 over 2 delta x? So it's basically, there's a point 2 here, there's a point 1 here, and there's a point 3 here. And I'm representing this slope as f3 minus f1 divided by 2 delta x over here. Why I'm writing it in a symmetric way, in a symmetric fashion? Because I want the matrix to be Hermitian. And it's going to be Hermitian. Look. Since this is the case, it's basically going to be, let me take h bar out, but leave I inside, because we want to see I inside. Let me take this 2 out, 2 delta x. And inside I have, for example, over here I have, let me think, just give me a moment. So for the second row, I have plus 1 here, minus 1 here, actually divided by I. So let me write it as minus I here, plus I here. Minus I here, plus I here. Minus I here, minus I here, plus I here, etc. And the rest is 0. Is this matrix Hermitian? Oh yeah. How about now? Is this Hermitian? Do you remember what Hermitian was? You needed the off diagonals to be complex conjugates of each other. Very good. This is just for you to understand the code. So let's look at the code. So the code starts by defining length unit to be angstrom. So whenever you see length here, it's in angstrom. Time is in femtoseconds. Energy is in electron volts. So what does this dt mean? It tells us that the time step is 0.1 femtoseconds. Okay? What is this? This is h bar, but in the units of electron volt times femtosecond, I want to say. Yes. H bar is energy times time, right? You agree with me a lot. Thank you. This is the mass of electron, which is kilograms in terms of this electron volts, femtoseconds, angstrom, whatever. And this is, what is this? This is Coulomb. Okay, we don't need this. We don't need this. But in case you, Coulomb constant multiplied by electron charge squared. We will need it when we do hydrogen atom. Right now we don't need it. Sure, always. Very good question. So you are telling me that.
So can we discuss the natural units business? I think this question is related to the natural units.
Okay, let's discuss it. You know that this is normally is the case, right? So I want to write kilogram in terms of energy, length, and time. How can I write it? So mv squared is energy, right? So kilogram times meter squared over second squared is joule. Do you follow this? So kilogram is joule times second squared over meter squared. So far so good? Right. So mass of electron is 9.1 times 10 to the minus 31 times joule times second squared over meter squared. Yes, you understand, but I want to continue torturing you. So this corresponds to 1 eV. So let's multiply it by 1 eV over 1.6 times 10 to the minus 19 joules, right? Multiply it by, yes, exactly. So second squared should be at the bottom, which corresponds 10 to the plus 30 femtosecond squared, right? They are equivalent. So far so good? And meter squared should be at the top. At the bottom should be 10 to the 20 angstrom squared. So far so good? So if you do all this calculation, if you make it all, you are going to get this number. Should we do it? No, right? Okay. Then there is this L. This is the size of the box. Box is 1 nanometer, which is 10 angstrom, right? Wow. I can actually write angstrom. What is N? N is number of grids, grid points. So I have divided 10 angstrom into 100 points, okay? Since I did that, I get the delta x from that, okay? L divided by n plus 1 is delta x. This is related to hydrogen atom. No, it's not related to hydrogen atom. It's actually related to kinetic energy terms. Do you see?
N plus 1.
Very good question. Very good question. I was going to answer it, discuss it only if someone asks. That's why it wasn't there. So what I'm doing here is that, where is the grid? I am naming this grid 0. This grid is 0, and the last grid is actually n plus 1. Okay, then you have then L is equal to m plus okay, let's do it with smaller stuff. So if you have 3 grid points, so this is the one that I'm dealing with, because this one is, I'm setting it to 0. Now I'm confusing you, but this is totally fine. In this case, n is 1, and I'm dividing it to n. Okay, let me just do it here. So let's say n is 5. N is 5. So I have this point that I'm not dealing with. So I'm not dealing with this point, but I'm interested in this one, this one, this one, this one, this one, and then this one is also 0. So I'm putting phi equals to 0 here, phi equals to 0 here, and it's not even entering my calculations. Okay. Then I have the point 1, 2, 3, 4, 5. Yes. And as you can see, the total length is L. And how many? What is delta x? Delta x is L over 5 plus 1, because there are 1, 2, 3, 4, 5, 6 steps. Huh? Yes. I'm plugging in the boundary conditions, and I'm dealing with this indexing of MATLAB, right? Because if it was Python, then the indexing would start at 0. There will be no problems, right? Very good. You got your answer. You are happy. Very good. So, for example, let's look at these matrices. So X is n by n of zeros, right? It starts like that, but then I put in the diagonals xn's. Do you see? Let me run this so that we get our matrices. It's this famous or infamous program. So if you look at X, it's basically some numbers in the diagonal. So 0.1, 0.2, 0.3, 0.4, etc. Right? Okay. Then what do I have at H? Hamiltonian. Hamiltonian should have every term. Look at the Hamiltonian. Look at the Hamiltonian. I basically have 1 minus 2, 1, 1 minus 2, 1, 1 minus 2, 1. And minus 2 is multiplied by this h bar squared over 2m delta x squared. So h bar squared over 2m delta x squared multiplied by those minus 2's, 1's, and 1's, etc. Blah, 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 blah. Okay? So that's how you construct your matrices. Let's do the following. Let me just put it in here. I'm going to plot for you something. And just ask questions if you have any. Evet, ama I'm going to use it just line width. Okay. Is that why it's putting this underscore there? Just hang in there. It will be all fine. So I'm going to find eigenvalues and eigenfunctions of the operator x. Okay. Then I'm going to plot each one, and let's see what happens. So this is the first eigenvector. As you can see, it's over here. Then I continue. The second one. Okay, one moment. The second one, third one, fourth, fifth, sixth. Do you see it? Some of you are sleeping. I think this was a bad idea. You were supposed to be, oh yes, now I understand. Anyone who is having that right now? Not even you? No? You? So this is operator x, and these are its eigenvectors. Okay? If you want, I can also write its eigenvalues. Let me write eigenvalue of n by n. So when I run this, do you see that the eigenvalue is this one, and as I move on, just moves on to other eigenvalues, right? Yes, you have a question.
Yeah, what does the function, dummy function do?
That's a dummy function.
I
Yeah, the only purpose of that one is to be dumb. I will come to that function. I have no idea what it does. It just doesn't work when I don't have that function.
You actually explained it in the other class.
Yeah, I know. The thing is that
In the Python.
when you know how I press something and it makes a measurement? It's needed for that thing just because I don't know that kind of coding. You know, I know this kind of coding, and then I just need MATLAB to do something like when I key press, do this, stop for a moment, and those kind of stuff I just find workarounds. This is a workaround. Doesn't matter. Look, Hamiltonian. Let me put it Hamiltonian. Okay, if the operator is Hamiltonian, look at the wave. Look at the eigenfunctions. This is the first one, right? What is the second one? How it should look? Yes, exactly. Second one, third one, fourth, fifth, etc. Yes? I change now and put it a momentum operator. Okay? It starts from this, which is apparently a wave that is moving to the left. Okay? And then it's another wave that's moving to the left, another wave that's moving to the left.
Why slight beating phenomenon?
Because it's basically representing a wave function going to the left. So it has a negative momentum. It's a wave function that's going to the left. And then as you go over those eigenfunctions, you reach at the other end, the wave function, the eigenfunction corresponding to the wave function going to the right. And this one is going to the right. It looks like the other one, right? Exactly similar. Yes? No. One is going to the left, one is going to the right.
Okay, but they should be similar.
They should be similar in shape, but there is a fundamental difference. Let me show you what's that difference. So, let me go with figure. So this is the first one. Okay, that's going to the left. And let me go to 100. This is the 100th one that's going to the right. What's the difference? Yeah, exactly. Exactly. You see, the red picks, which correspond to real part of the wave function, are on the right-hand side of the imaginary part, while here they are on the left-hand side. So this, if you start like this, it will go to the left. If you start like this, it will go to the right. What do you mean?
Which one is red?
I'm sorry. I'm sorry. So, would you be able to do blue and green?
Yes.
Yes, let's do blue and green. Very good. Inclusive. Now the others don't see it. You have superpowers.
Sağdaki sola giden olsun.
Yeah, whatever. Like one of them is like that, one of them is like this. Thank you.
They are following the imaginary, right?
Yeah, exactly. So that's the difference between a wave that's going to the right and going to the left. It's basically e to the ikx and e to the minus ikx. All right. So what? Let's look at the, so far we have seen the, okay, I can't stop it. Yeah. So far, we have seen the matrices, right? And hopefully you have seen that each one of them has its own set of eigenvalues and eigenfunctions. Now, what is this one? Let me explain what is that one doing. So that one is basically, this is my Schrödinger equation, right? I h bar del psi over del t equals h psi, right? I can write it like this. Del psi over del t is equal to h over I h bar psi. So far, so good? Let me remember what was happening here. Yeah, so if I want del psi over psi is equal to h over I h bar del t, integrate, and you are going to get psi at t plus delta t is equal to psi at t, but operated by e to the h over I h bar delta t matrix times psi at t. So this is where you go. So this is what it is doing. So let's look at this. It has minus I. Minus I is fine. It's minus I is this one, right? So this whole thing is a matrix, actually. Do you remember matrices being at the top of the exponential, right at the beginning of the lectures? So whenever you have that, you don't write exp, but you do write exp_m. Do you see it? It's different from exp. Do you remember how it was different? No?
It's related to multiple semi-Clara series.
Yes. Yes, exactly. Exp_m, is that why it is m or because of matrix? So when you have this one, you have basically identity plus 1 over 1 factorial a plus 1 over 2 factorial a squared, blah, blah, blah. Okay? Look at how Schrödinger equation is written here. This is the Schrödinger equation. This is the Schrödinger equation for this code. Anyways, I couldn't write Schrödinger. Because it takes current F and operates on it by U, which takes it to the next time step. Okay, that's pretty much it. Okay, that's how you get this shaking wave function. That's how you get this moving wave function. How about measurement? This is where you have the measurement. In the case of the measurement, you are measuring some operator, right? What it does is it first finds its eigenvector and eigenvalues, right? Okay, you are too bored for me to go over this. And then figures out the probability of each one coming up, etc. You are too bored, I will stop. Hopefully you understood something from this. And let me move to something way more boring. Okay? Let's move to something way more boring. So we discussed quantum mechanics. We know we have the Schrödinger's equation. How many systems have we solved so far with our hands? One particle in a box, okay? And I promised you that you are going to just be able to solve 2 systems. maybe a little bit of hydrogen. Okay, so this is the second system. It's quantum harmonic oscillator. Okay. Now, as I promised, it will be boring, tedious work. So let me give you the result at the beginning. Okay? Let me give you the result at the beginning. So particle in a box, resulted in these energy levels that look like this, right? It was E0, 4E0, 9E0, etc. Right? Now, what do we expect from quantum harmonic oscillator? Sure. What do we expect according to Planck? After all these years, after 25 years, 26 years, now we need to have an explanation for this, for the effect that started all this story, right? Do you remember the story? Started with ultraviolet catastrophe, and Planck said something crazy, that oscillators shouldn't have just any energy they want to have, but it should be related to frequency, right? Should be related to frequency. So this was Planck's formula, right? NHF, and it worked, right? Well, we will figure out full solution using Schrödinger's equation, and we are going to get this. Okay? Just it's the same, so it still works. Whatever Planck said is still valid, right? Despite this zero level oscillation. So what we are going to get is HF over 2, HF, 3HF over 2, 5HF over 2. Can you compare these two? This one is equally spaced, the other one is going like a square. And this one had eigenfunctions that look like this, right? This one will be actually very similar. It's just going to start with a Gaussian, like this, and something like this, and then something like this. That's where we are going with this. Tim, it's not zero at the edges because, look, this one is bounded between 0 and A, right? So the particle actually has to go to 0 at the edges. But for the quantum harmonic oscillator, it can in principle go forever to the minus infinity and to the plus infinity. So our integrals in particle in a box were going from 0 to A. Now they are going to go from minus infinity to plus infinity. Okay? Do you have any questions? Any comments? So what is changed when you go from particle in a box to harmonic oscillator? What is the main change? The potential is not 0 anymore, right? What is the potential energy? It's basically kx squared over 2, right? Do you agree with that? It's harmonic oscillator. Do you remember potential energy of harmonic oscillator? Kx squared over 2. That's it. That's the only change here. So our potential is kx squared over 2 and we have omega angular frequency, which is square root k over m. You remember this from the classical mechanics part, right? And we are going to solve time independent Schrödinger equation. So we are not bothering ourselves with time dependent one anymore, because we know that we are going to find hf ef from this, right? H phi E phi. So how does h look like? H still has this minus h bar squared over 2m d squared over dx squared, but it also has this kx squared over 2. Right? Let me rewrite it as p squared over 2m plus m squared w squared x squared over 2. Now we are going to solve this harmonic oscillator in a very different way. Okay? Do you remember this? A squared minus b squared used to be a plus b, a minus b. Do you remember this? What if you have a squared plus b squared? Very good. So you can go with a plus ib times a minus ib. That's the sort of thing that we are going to do here. Okay? What?
I see where it's going now.
You see where it's going now? Okay. It's a long story, and I will do it this time. I will do it this time. Do you need a break right now? Please, after the break, be more fresh, because it will take a lot of mental faculties to